detail for the homework and the formula sheet for the op-amps, which will be covered in the assignment 3 and for the last test of this course. Now, going back to what we discussed in the applications for the op-amps, we discussed and we took, the basic of non-inverting amplifier and the inverting amplifier. And I mentioned that, basically, most of the or all the applications that are used, it uses, these two basic configurations as the non-inverting or inverting amplifier. Remember that a voltage follower, it's a special case or a particular case of a non-inverting amplifier, making the RF, RI as 0 or and infinite resistance. On the other basic applications, there are hundreds of applications of the op-amps, but I'll focus on just few of them, because probably most of the applications derives from any of these or an alteration of any of these basic applications for the op-amps. The other applications that I will talk about is a comparator, a summing amplifier, an integrator, and differentiator. To remind you what the characteristics and the basic operation of an op-amp does not change. The only thing that is changed is how to use them. And I will show you, the last note, that I put, before I'm going into the other applications, that the comparator, the summing amplifier, integrator, and differentiator uses one of the two basic configurations or the two basic circuits, non-inverting or an inverting amplifier. Now, a comparator, what a comparator does, it will compare, the two voltages, or it will compare, or it will have, the comparison between the input, or one of the two input voltage as the reference and the other voltage as a variable or a changeable voltage. Now, to give you an idea about, where we can use a comparator, suppose that we are using, in instrumentation, we want to trigger an alarm that is above, a temperature. Most of the time, these comparators can be used in measuring pressure, measuring temperature, measuring the level in a tank. Means that there are specific applications where we may see a comparator that is used to trigger an alarm or to trigger a buzzer or turning on a light showing that the certain level or certain temperature is above a certain value. Now, how we can use that? We can use the open loop gain. Remember that the open loop gain for an op-amp is a very high number or very large open loop gain. Again, it's about greater than 100,000. Means that an op-amp can detect or can it's sensitive to a very tiny difference between the two inputs. Now, special type of comparators, they are integrated circuits that are called comparators, which are specially designed to be used as a comparator. But a comparator cannot be used as an op-amp, but an op-amp can be used as a comparator. Again, make sure that you are not using a comparator as an op-amp. In lab that we are doing, the last lab, which is lab 10, I'm using actually a special type of the op-amps, which is a comparator, which has a higher gain, and the time or the response time of the comparators is faster than the regular op amps, and that's specific for a comparator. Now we'll take just few examples or how to use op amp as a zero level detection. Again, we'll do the same thing in the last lab, but we are using a comparator. But at this point, just using a basic op amp, we are looking, to find a configuration or a basic circuit that it will detect any voltages that crosses zero. That's why it's called the zero level detector or zero level comparator. Now, how to use that is one of the two inputs is grounded, means that it will act as the reference voltage, and the input voltage or the Vin is applied to a non-inverting input. You notice that this configuration is actually a non-inverting amplifier. That's specific for the op amp, which will amplify the difference between the two inputs. Remember that we talk about the difference between the two inputs, but the input voltage on the inverting input is grounded, means that for any voltages Vin above or higher than the ground level, the output voltage, it will be changed to another state. Now, in this example, you notice that I'm applying a sine wave or a variable input voltage, not just the sine wave, just a variable input voltage, as the input voltage or the Vin is just tiny bit greater than the reference voltage. And you notice that again the reference voltage is zero level or it's grounded. For any voltages applied on the input, non-inverting input, greater than the zero voltage, the state of the output voltage, it will be changed from the negative maximum to the negative to the positive maximum. Remember that the open loop gain, you notice that there is no feedback network or feedback resistance between the input and the output. Means that the gain of an open circuit or AOL, open loop gain, being very high, it will saturate the output voltage to the maximum. Remember that the maximum output voltage is actually based on the applied voltage, and remember that we have the two voltages. One is the positive, the other one is the negative. Means that rail to rail or the output voltage can be swing between the negative voltage, applied voltage to the op amp, to the maximum positive voltage. Sometimes, it can be, 10 volts, 12 volts, 15 volts, 18 volts, 20 volts. Means that the output voltage or the swing or the maximum voltage on the saturation of the op amp, it's the based on the applied voltage to the op amp. And being a non-inverting amplifier means that the phase shift between the input and the output is equal to zero, or there is no phase shift between the output and the input. Excuse me. Going back to the initial state, if the voltage Vin is greater, just tiny above the zero voltage or the reference voltage, which is zero or ground, the output voltage, it will be reach the maximum or the saturation. For any other voltages greater than zero, it will stay on the maximum saturation voltage. If the Vin is less than zero, you notice that at this point, if the Vin, or when the voltage is going just tiny below the zero voltage, the output of the op amp, it will change to the maximum negative. You notice that again, if the input voltage is negative, the maximum the output voltage it's negative, but having an open loop gain goes to the maximum negative voltage. Again, where we can use that as an application. Suppose that we want to, convert, and that's, a very practical application. If we are looking to convert a sine wave or a waveform that has, a variable AC voltage into a square wave, and that's, actually a practical application in the function generators. You notice that the function generator has, the sine wave output can have, the rectangular waveform output. Means that by simply using an op-amp with no feedback network or using, the largest or the highest gain for the circuit, I can convert, I can I can transform, let's say, a sine wave into a rectangular waveform. Now, suppose that I'm looking, to have, the same circuit, but I'm not looking, to have, the zero level detector. Suppose that I want to make, or I want to trigger, I want to change the state of the output when the voltage is greater than 4 volts or 5 volts or 10 volts. What can we use? You notice that one of the applications that uses a Zener diode is connecting, the Zener diode through a resistor to the positive of the voltage source. You notice that the Zener diode is in reverse bias, means that connecting the non-inverting input or the reference voltage, which is actually the VZ, to the inverting input, I will change the reference voltage from 0 volts to the VREF. Again, the VREF or the reference voltage is the same in this example with the VZ. Excuse me. Means that choosing a different Zener diodes. Again, those are standardized voltages or standardized values for the Zener diodes. I'm starting with 1.2, 1.8, around 5 volts is 4.7, 5.1, 5.8, 6.2. Those are standardized values for the VZ. I can choose a different Zener. I can choose a different reference level. Means that applying any voltages above the reference level, which is in this case the VZ, I will change the state of the output of the op-amp. If there are any voltages or the Vin is less than the VZ or the reference voltage, the output of the op-amp goes, on the negative side, means that it will reach or it will stay on the saturation negative value if the voltage is less than the reference voltage. In the same way, we can create a reference voltage, but on the negative side. You notice that in this example, in this diagram, shows that the reference voltage is chosen as a positive value. In the same way, I can choose the reference voltage on the negative value by simply switching, the positive of one of the two voltages to a negative voltage. Means that I can choose in a reverse way. I can choose, the reference voltage as a negative voltage, and what is going to happen with the output voltage? It will be changed, in opposite way. Means that the output will be negative for any voltages below the input, and it will be positive for any voltages above the reference voltage. What is the inconvenience of this circuit? And I mentioned that the VZ comes in a standardized values. But let's make an example. Suppose that I need a reference voltage that has to be precise value as 5.25. That's, a very hard way, to get a Zener diode that has the reference voltage or the VZ as 5.25. Usually it's, 5.1 or 5.8. If I need, any other voltages which is between those values, it's very hard to obtain, these values. A practical way is replacing the Zener diode with a resistor. And we'll end up with the second configuration, means that I'm using, a voltage divider. You notice that the R1 is in series with R2 by choosing, the value for the R1 and R2, and we know how to choose how to calculate the reference voltage. The reference voltage is the voltage across R2. The voltage across R1 means that the voltage divider rule applied for a series type circuit is the R2 over the R1 plus R2. You notice that in this equation, I emphasize, how to calculate or how to determine what is the reference voltage. Suppose that, as in, our previous example, I choose to have, the reference voltage as 5.25. And I will choose, the value for the resistors R1 means that I have, a single equation, a single unknown as to find the resistance R2. Means that that's, the easiest way to determine the value of the resistance R2 for an imposed reference voltage or choosing, one of the two resistances. Another practical application is using a variable voltage source. Again, if we have, a variable voltage source, and I'll put, the variable voltage source symbol aside. Suppose that we want to use, a variable voltage source, means that does not require any other external devices. But this case or this, condition is not always available. Is not always available a variable voltage source. If we have to change constantly the reference voltage, we may use a potentiometer or we may use a trimmer, which is a variable resistor. And I will add, in this diagram, a variable resistor, which is a potentiometer or a trimmer. In this way, we can make, a fine adjustment of the reference voltage by simply changing the resistance R2. I will not suggest, to have both resistors change, just one of the two. And if you're looking, in this equation, because the R2 is on numerator and denominator, I would suggest to change the resistance R2 instead of changing the resistance R1. And I mentioned that if is require a standardized value for the reference as 4.7, 5.1, 6.2, 6.8, 7.2, those are standardized voltages, we may use a Zener diode. The easiest way, most practical way, most of the time I use the voltage divider or two resistors connected in series, calculate, or choose, one of them, and I will calculate the resistance R2. That's, a very practical example, simple way to choose, the reference voltage or to adjust the reference voltage by simply changing or adjusting the resistance R1 or R2. Now, what is the output? Again, if the input voltage is greater than the reference voltage, it will change the state of the output of the op-amp. In the same way, if the input voltage is less than the reference voltage, being a non-inverting amplifier, the output voltage goes lower, or it will be the maximum negative voltage. Remember that is the maximum negative because the op amp is supplied by the two voltages, the positive and the negative voltage, and has no feedback resistance or no RF and the RI. Now, another applications which derives, from using, different diodes. In this example, we use the Zener diode, which is, if is connected as the RF or the feedback resistance, or instead of the feedback resistance, it will limit the output voltage. In some applications, when the output voltage is required to be limited to 5 volts, to 10 volts, to 8 volts, any of these values, we can use a Zener diode connected in the feedback or the negative, or as the negative feedback of the op amp, means that the positive or the non-inverting input of the op amp is grounded or it's connected to the ground. The RI is the input resistance, and the RF is replaced with a Zener diode. Again, what a Zener diode does, it will limit the amplitude or the level of the output voltage. Remember that the Zener diode works when the positive is applied on the cathode and the negative is applied on the anode. But remember that we talk about the potential or the virtual zero level at the inverting input of the op amp, because the other input is grounded. Means that the Zener diode is connected to the ground level or a virtual 0 volts, and based on the based on the level of the output voltage, the diode may act as a regular diode, which means that the positive potential is applied on the anode and a negative potential is applied to the cathode. In this case, the Zener diode, it will act as a regular diode, means that it's forward bias. In opposite way, if the output is negative or it's going to the negative value, means that I'm applying a more negative value on the cathode and a positive value on the anode, which will act as the regular diode. And in opposite way, if the output voltage is positive and the cathode means that it's connected to a positive voltage, the anode to a negative voltage, the diode is in reverse bias, means that it will act as a Zener diode, which will limit the output voltage to the VZ or the voltage across the diode. Now, if we are applying an AC voltage, I mentioned that you notice that is an inverting amplifier. The input voltage is applied on the inverting input. Means that the output voltage is 180 degrees out of phase with the input voltage for an increase or for a voltage above 0, or as a positive voltage is applied to the input, the output voltage goes on the negative on the negative side, or the negative voltage. If a negative voltage again is applied on the cathode, the anode is connected to 0, means that I'm applying, a negative potential on the cathode and a more positive potential on the anode, means that the diode, it will act as a regular diode. It's a forward biased diode, means that the voltage across the diode is 0.7, means that the output voltage is at the 0.7 level voltage due to the fact that the diode is acting or is in forward biased. If the voltage is below the x-axis, or it will have a negative voltage applied to it. If the voltage is negative, the output will be positive. Means that now I'm applying a positive voltage on the cathode, and the anode is connected to a zero or the virtual ground. Means that the diode is in forward bias, means that it will act as a Zener diode, which will limit the output voltage or the output voltage of the op amp to the Zener voltage. Means that the output voltage of the op amp is limited to the VZ value. Again, can be any of these standardized voltages, 2 volts, 3 volts, 5 volts, 10 volts, and so on. Now, suppose that I'm using, the same diode, the same Zener diode, but in opposite way. Suppose that I'm changing the polarity of the Zener diode. What is going to happen? It will limit the output voltage, but on the negative side. Means that everything stays the same. Everything, is switched, in the same way, except that this time, the voltage will be limited to a negative VZ when the Zener diode is reversed. Now, based on these two circuits, now let's have a look, how the circuit it will behave if I'm combining, if I'm connecting those two diodes, back to back. Now, if the two diodes, or D1, D2, are connected back to back, the output voltage, it will be limited between the two values, is the VZ plus the 0.7 and the VZ1 minus the 0.7. From where is coming, the 0.7? Again, if the output voltage is positive, the D2 it's in reverse bias, and D1 is in forward bias. Means that the voltage across D2 plus the 0.7 volts, which is the voltage across D1. If the output voltage is negative, if the negative voltage is applied on the it's on the output, the D1 is forward bias and D2 is in reverse bias. Means that the output voltage, it will be limited to one of the two Zener voltages plus the 0.7 volts due to the other diode, which will be in reverse, in forward bias. Now we may have, to choose, the D1 equals or identical with D2. In this case, I have a similar voltage on the positive and a similar voltage on the negative. In the same way, we may choose, different values for the D1 and D2. Means that using, the same circuit, we can have, a pretty good, ways, to change the value of the D1 and D2 and getting, different amplitudes of the output voltage. Depends on, what is required, what is used, for these circuits. Now, going on the summing amplifier. Remember, I mentioned that, one of the specific applications is for basic math or mathematical applications, summing, multiplication, integration, differentiation, and so on. Summing amplifier. Now, suppose that I'm using, the multiple input voltages, Vin1, Vin2, Vin3, and so on. And we want to have the sum of all these input voltages. Means that I have to use the amplifier as a summing circuit or a summing amplifier. can have, two or more inputs. The output voltage is a negative algebraic sum of the inputs. You notice that the signal or the input voltages are applied on the inverting input, means that the output is out of phase with the input voltage and the phase angle is 180 degrees. Now, I'll take, just an example how to approach or how to determine the input voltage. I will take, just a single input as we did before and the RF. You notice that if I'm choosing, the R in and the RF to calculate the output voltage being an inverting amplifier is the negative R over the I. But the I, which is the total current, is the sum of two, branch currents, I1 and the I2, means that I can do, the same approach, choosing the second input voltage or the second resistance, the second input voltage, and the same RF. You notice that the RF stays the same or is the common resistance for all the other inputs. Means that I can calculate, the IT as the sum of the two currents, replacing the currents with the voltage and resistance one or the and the resistance R. I can determine or I can find voltage as the input voltages of and to actually base to inputs I want to multiply by RF. Sorry, could you hear this? No? Can you hear me? We may please the thing, guys. Not trying, to connect to the thing or that goes. I can restart the team meeting. Well, should we continue this way? As you know, the problem. Not. I will speed up meeting. I will start meeting and I will restart. Meeting probably will get connection. I agree with that. Yes. Well, I'll hang out. Great. Could you hear me now? Clear enough? Still happy? Okay, I will try one time. I will close and open up the Teams, see if it's some application, something on the calling server. I have here. I will start this meeting again. Happy? Could you hear me, guys? Seems a bit better. Okay, let's go back to again from my side. Looks like everything is well, but I don't know from your side. Now let's look back and How about now? Is it now? Could you put in chat? Hey guys. It's still again. I know yesterday they made a change in the server and the I just an email. I don't know. Still, our connection passes. I don't mind. I just the connections and it's really strong. I don't have problems. Why? Anyway, let's try to continue to see what we today. We took up the summing amplifier, which amplifies the sum of the two voltage. The voltage, input voltage V over the resistance R plus the V over the resistance R2 by R. An example when we are to make between the three inputs, so that I have the voltages, the and all resistors 10 kilo ohms. Means that the resistors 1 or 2 are in value. That we reduce simplification and will end up with the amplifier which will sum the in voltages. Means that the output is a algebraic of all the input voltages, but get negatives because it's putting this equation, if we're taking R1 equals R2 equals RF equals a given resistance, it doesn't matter. All the voltage is that inverting amplifier, this two input voltage. Now, so that we are looking to have a summing amplifier with a unity gain, and actually the condition to have unity, it will have the sum or bracket of all the input voltage with the negative sign in front. The condition of having summing amplifier with an unity gain means that if all resistors or all n resistors and the R a summing amplifier with a gain. The summing amplifier with a given gain. Suppose that a greater, if the gain is greater than 1, and have a summing amplifier by simply using the equation, have the R over the resistance, because we placing the resistance, or we choosing the resistance R equals R equals R on, and if we are making a range of the RF resistance greater than 1, we'll still have a summing amplifier with a of 2, 3, or 4, and so on, where it's equal. Means that a different value for RF is different resistance 1, 2, 3, on, and end up summing amplifier is a gain greater than the amplifier. Now let's have on the how we can for the suppose that and now suppose that I have 2 inputs. Have the average of 2 inputs and divide the 2 inputs by means that I have to make the average of RF, the R is equal to over 2. But based on the number of inputs, you have an average. If I will make the rate of the RF and distance R as 1 in the number of the inputs, I can convert this based into average amplifier. Is that amplify the average between or multiple inputs? If we have 3 inputs, suppose that 3 inputs means that I need the ratio RF over distance is equal. Suppose that I have to convert RF over resistance R equals 3 over 4. So on. And that example shows that the output which seeing 3 voltages and the amplifier means that the equals R 3. So is the R is 3. Is that the F over I? That RF over I, which makes 1 over 2. This sign becomes an inverting amplifier and will end up with negative 1.9 volts at the average amplifier. The 3 input voltages, that's V1, that's V2, the V3. Now, a second amplifier derived from the previous, which is an average amplifier or average amplifier. If we are changing in a ratio of the gain of each input, suppose that I'm using equivalent ratio RF over RI, R over R2, RF over RN is that I'm choosing different for different input voltages. So I put